Okay, folks, now that we've tried a couple of simpler buffer problems, just calculating pH, given some information, we're going to work a problem that's a little bit more involved. It's not that much more difficult, there's just more steps to do. So in this problem, we're going to take some information and calculate a buffer pH, and then after we do that, we're going to add a little bit of either an acid or a base and see what happens to the pH upon adding a little bit of an acid or a base to our buffer. So here's our setup. We've got 100 mils of a buffer. And this buffer has 0.25 molar A minus and 2.25 molar HA and a Ka of, well, we'll do a pKa. The pKa is 6.10. So 0.25 molar A minus, 2.25 molar HA, and a pKa of 6.10. That's our initial setup. So we're going to first calculate the pH of that buffer. So that comes from the Henderson-Hasselbalch equation. pH is equal to the pKa plus the log concentration of A minus over the concentration of HA. Plugging in our numbers, it equals 6.10 plus the log of A minus, which was 0.25, over HA, which is 2.25. So working that one out, try that log term first. It'll be easier on these calculators. So 0.25 divided by 2.25 equals 0.111. The log of that minus 0.95 plus 6.1. So the pH of this buffer should be 5.14. So that's just the standard kind of buffer problem. pH went down because the acid concentration was higher than the base concentration, so it went down from pKa. Okay, now we hit up the next step in these kinds of problems. We're going to add a little bit of sodium hydroxide to this buffer and see what happens to the pH because of that. So to this buffer, we're going to add 5 mils of 0.50 molar NaOH. So now our job is to calculate the new pH. Well, the pKa didn't change. We're just changing the ratio of A minus to HA. That changes because of our added base. We added a base that consumed some H+. So the pH is going to go up because we did this, but it's not going to go up a large amount. It's a relatively minor amount because of the buffer. So to calculate the new pH, we need to know how many moles of A minus and HA are present now in the solution after adding this. So we're going to work this buffer problem in moles because we're going to need to calculate moles first. If we want to go to molarity, we could, but it's not necessary because like we've mentioned before, we can work the Henderson-Hasselbalch equations in moles of A minus over moles of HA. So moles of A minus, we're going to calculate that by taking our 0.100 liters of buffer, our 100 mils of buffer, 0.1 liters, and there were 0.250 moles of A minus per 1 liter of buffer. So that's how many moles of A minus we had to start. And then we're going to subtract the number of moles of A minus that have been eaten up by that have been generated by conversion to A minus from the NaOH addition. So we're going to add a certain number of moles of A minus because we've added a base. So we're going to add 5.00 milliliters of NaOH, and in every 1,000 milliliters of NaOH, we have 0.50 moles of NaOH. And then I'll squeeze in right here at the edge of the screen. For every 1 mole of NaOH, we generate 1 mole of A minus, because all of our buffers are based on monoprotic acid base equilibria. So this calculation right here tells us how many moles of A minus are present after we added our 5 mils of NaOH. So we have on our calculator 0.1 times 0.25 plus 5 times 0.5 divided by 1,000. So we have 0.0275. Moles of A minus right now. Repeat that calculation for moles of HA. The moles of HA are going to decrease because we added a base. That base is going to remove some moles of HA. So we started out with 0.100 liters of solution, and every 1 liter of solution, we had 2.25 moles of HA. So that's our starting amount of HA. Now we're going to be subtracting some HA because of the addition of the base. So minus 5.00 milliliters of NaOH, and every 1,000 milliliters of NaOH, using the molarity, that is 0.50 moles of NaOH. And for every 1 mole of NaOH that goes in, we generate 1 mole of HA, or consume 1 mole of HA. So we calculate that through 0.1 times 2.25 minus 5 times 0.5 divided by 1,000. 0.2225. Now we have everything we need to calculate the pH of this buffer as it stands right now. We have the pKa from the problem and our new number of moles. So pH is equal to 6.10 plus the log. Our A minus concentration is now 0.0275. Well, moles now, not concentration. And our moles of HA, 0.2225. So again, doing the log term first, 0.0275 divided by 0.2225 equals 0.214 on my screen. Log of that, minus 0.908 plus 6.1. pH is 5.19. So the pH went up just a little bit. The original buffer, 5.14, we had a little bit of base. The concentration of A minus went up, and our pH went up just slightly. So because of the buffer, this pH didn't change very much. So while we've got our numbers here to look at, let's compare how this would be adding 5 mils of NaOH at half molar concentration to 100 mils of water. This one's a dilution, because if we just added it without the buffer being present, we're just adding it to water. So M1 B1 equals M2 B2. Final concentration is M1 times V1 over V2. So we plug in our numbers. Our initial molarity, 0.50 molar, and our initial volume, 5.00 milliliters over 100. milliliters. This gives us M2 to be 0.5 times 5 divided by 100, 0.025 molar. That molar is OH minus because this is an NaOH solution, right? So that's a concentration of OH minus, which means that the POH is the negative log of OH minus. So it's on my screen now. I just hit log and flip the sign, 1.60. And the pH is 14 minus POH, which again, hopefully remember learning that one before we dismissed for virus issues. So 14 minus 1.6, 12.4. So let's take a look at our numbers here. If we added 5 mils of NaOH to the buffer, then the pH jumps 0.05 units, so 5.14 to 5.19. If we add that same amount of NaOH to pure water, the pH jumps by almost 5.5 units. It goes from pH 7 for pure water up to 12.4. That's the true buffering concept as far as conjugate acid bases go. When you have a bunch of each, then the changes in pH are much, much less than you would expect just for adding it to pure water. Okay? This is the harder kind of buffer problem. If you can work this one, you can probably work them all. Because again, it required us to work the simple version first. We had to work the simple version to get this initial pH, and then we reworked it after adding something to it. If we had added an acid instead of a base, we'd still have to work the same kinds of things out. How much A minus is there? We've been subtracting here because the acid would remove some A minus. And for HA, we would have been adding here because adding an acid would push equilibrium to the left and create more HA. But that's the only difference. We still plug in our answers into the Hessian-Hasselbalch and figure out our pH. All right, good luck, folks.